Okay, let's get started. So this is a short summary on model-free reinforcement learning as we have seen it in the last two lectures. If you already feel comfortable with all the methods and you think that you intuitively understood them, you might also skip this lecture and it will not provide you any more information. Okay, so where did we actually start? So we started with dynamic programming methods to find optimal controllers. And we have seen that dynamic programming methods are guaranteed to find optimal solutions for both Q and V in polynomial time, in number of states and actions, and that they are exponentially faster than a direct search. Policy iteration computes the value function under a given policy, and we use then the given policy to improve the policy while the value iteration directly worked on the state values. Both of these, or most of the methods that we have seen then so far, they performed sweeps over the state set, they implemented the Bellman equation update, and they used bootstrapping, meaning that they iteratively updated their knowledge of the state values. However, they required a complete and accurate model of the environment, which makes them very limited in their practical applicability, as we usually do not know the dynamics of the environment, or we do not accurately enough are able to accurately enough describe them. So we introduced the Generalized Policy Iteration Framework, which is actually a framework that actually helped us to finally, in the end, understand how model-free control works. And we iteratively updated this framework to actually work on that. The basic idea was to say that we have two interleaving steps of policy evaluation and policy improvement. The policy evaluation step estimates a value function under a policy pi, and the policy improvement step improves the policy by taking argmax operations over the estimated value function. And through this interleaving updates, we actually end up with the optimal value function and the optimal policy. As simple steps, if we used it with dynamic programming, we had policy iteration as an example. We have iterative policy evaluation, where we evaluated the policy by just executing it. And then we had greedy policy improvement by just taking the one-step probability transition times the discounted value of the next states. Then we said it is problematic maybe that in practice we do not actually know the MDP, or we actually know that there is an MDP, but we do not have full knowledge on the MDP, meaning that we do not actually know what P and R is, or both. Nobody tells us exactly how the environment works, but we usually have some means of interaction possibility through our agent environment interface, where we have an agent that can actually execute actions and receive feedback from the environment. While doing this, we are actually differentiating between two problems on unknown MDPs. The first one was model-free prediction. Basically, the goal behind model-free prediction is to evaluate the future given the policy pi. So we want to estimate the value function. And model-free control deals with the problem of optimizing the futures by finding the best policy pi, which is actually optimizing the value function. Then we actually got to know two methods to evaluate a policy or to do model-free prediction. And the first one was time difference learning, in this case with a one-step look ahead, versus Monte Carlo policy evaluation. Both of them have the goal to learn the value function v pi online only through experience samples that we get following a policy pi. And we have seen also the difference that the update, that actually we get experience samples from the environment from which we actually estimate the return G. So actually we know an experience trajectory in Monte Carlo, and we can estimate for each state for this sample the return. And through incrementing visiting counters and getting knowledge about the return, we can always update in an online fashion our estimation of our value function. So there was also a way of doing this with absolute examples, but we derived an incremental way of doing this. And we also have seen that in non-stationary problems, it's not always a nice thing to just refrain to the visitation counter, but also to have some small value that we can treat something like an update as something like an update rate. And from this, we derived the general update estimation update, which is simply saying that our new estimate is our old estimate plus some step size that reduces the error, which is the target minus the old estimate. Then we saw that in Monte Carlo we are actually using the sample return, so we actually had the full trajectory, and for each of the state in the trajectory we could actually calculate the real return. But this is something that's also very limited. It limits us in the applicability in practice, because we always have to wait until an episode ends to learn something. There is a lot of real life examples that we also have seen in the lecture where this is actually also a very motivating thing. So if you play chess and you perform actions that you know that end up in a bad situation, that actually this is something that you always think that bad is already an estimate. So the thing is, you do not really play the game until the end in order to know that the board state currently is a bad state, because you already knew that. So in this example, it would actually be that if you play chess and you perform an action and you end up in a bad situation, and then the fire alarm goes out and you have to go, you wouldn't actually need, so you in this case would never find out that this is a bad situation, because you actually did not terminate the game. However, if you do TD learning, you already would have known that this is a bad state. The next example would be you're driving a car, and from other policies you know that certain kinds of episodes lead to a death. And now if you're encountering a state that is close to some of those states that you have seen, you already have an estimate that you're currently not doing so well. So actually, in order to learn that that ending up in this state was not good, you immediately can learn from it. You do not need to actually die in order to update your value function to know that the state was bad. You already know it, and you can update it like incrementally and bootstrap the information. The next one was you look into the oven, you see a burnt cake. This is also something that you do in practice. You do not really need to taste it. You already know that the sequence of action that lead to a burnt cake is not a good sequence, because the burnt cake will not taste well. And also we have seen the riding home example. So you encounter different places, and you already can learn from single steps if you encountered that state sequence before. So we as humans usually do 3D learning in practice, and at some points we call this intuition, because we have an intuition understanding what a bad or a good situation is. And and we clearly also use some ideas and transfer learn from that situations. Which leads us actually to do Monte Carlo to do model-free prediction using time difference learning, where we said, okay, we do not update our value function with respect to the experience sample or to the actual return of the state, but to our estimate of the return of the state. And the estimate of the return of our state is the immediate reward we get to the next state, plus the discounted value of the next state the discounted estimated value that we use of the next state, which is basically the intuitive understanding of the oven example and the driving example. And everything else just keeps as it is. We also have seen that most of the problems can be described by MDPs, and this is actually also why this works much more sample efficient, much better in practice. I already have talked 2 times about this example, but the main idea behind the example was that with limited experience, you can get to the correct estimate of the value function quickly, and in practice it is not always a good idea to infinitely often sample the environment to actually converge to the right values. And if the world is described by an MDP, using TD learning actually converges to the correct values much faster than Monte Carlo learning. We also have seen the visualization of our update functions, which we can actually do through backup diagrams. Such a backup diagrams just describes states. So this is the state st that we are in, and the black dots are actually actions that we can take, and we end up in next states, take actions until some terminal states. And we can visualize how we actually bootstrap or update our value function st, and what kind of information we actually use to update our value function st. And we have seen that the backup of the dynamic programming, in the dynamic programming when we use value iteration or policy iteration, it just in order to update st, it uses or it incorporates all the information to the successor state, with respect also the probability transitions and the actions that we can take to reach the successor states. In the Monte Carlo backup, what we usually do is we start in a state and we run a trajectory, and then we use all the states we visited along and update these states along our trajectory. Meaning that we will make use, in order to update st, all the information we get until we reach the terminal state. And in contrast, our the time difference learning backup is something like in between. We use the way of running episodes in the environment, but we always bootstrap our information of st only depending on an estimate of the next state and not a real experience sample. And we update, so we actually also have seen that we say we update our guess towards a guess. So we have then seen that if we want to do model-free control, we cannot just simply go on with simple ideas to do the policy improvement. Because if we actually estimate the value function v and we want to do the argmax policy improvement, this required actually, you see it on this slide, this required actually the knowledge about our probability transition matrix. But we also had, in a sense, seen that we also have seen that we discussed the state value function in the beginning, where we always derived our formulas from it, but we also have seen our state action value function q, which is basically incorporating a one-step look ahead in our state value estimations. So in this case, you see that the q function, so the expected return that we are in this state and we select action A, is 0.85, which is nothing else than the state value that we have in here if we follow our policy pi that uses the argmax operation in here. So if we actually estimate the q function instead of the v function, which we do in here, we can actually use it to directly do an argmax operation over the estimated q values in our table, which does not actually need to directly use the probability transition matrix to actually calculate it. However, the second problem that arises in here was that the second problem that actually arises in the in the greedy policy improvement step was the problem of exploration. So the problem, if we're always if you're just estimating our value function, and if our policy is always greedy with respect to our value function, we will never explore the state space that doesn't look so good in the first sense. So if we have in the first sense some bad information of our state, we will always select state and action sequences from which we know the return, and this is the maximum that we have seen so far. We will always keep on selecting this one. We have seen the example with the job interview where you have two doors to choose from, and both of these doors have different rewards associated with them. And if we are like sampling the environment, we actually sample from the random variable that is describing the reward behind of these doors. And now imagine that the rewards behind the left door is something like a Gaussian that has a mean around 50 and like a large variance. And if you just open it and you sample from this Gaussian, you just get a 0. Yeah, so you actually get a 0 reward for it. And so far, after the first step, you have no reward gotten so far for the right one. So in the next iteration, you will select the right door, and maybe the right door has also a random process associated with it, like a Gaussian with a 0 mean and a 1 variance, and you get a reward of 1, meaning that the state value of the right door is larger, and you will keep on selecting the right door because it always maximizes your current, it also from the current state of knowledge, it always maximizes your return. And the question is, are you sure you have selected the best door? And this is the problem of exploration exploitation, where you always try to learn more about the environment in order to, so you explore the environment, and where you need to exploit the environment in order to maximize your return. Okay, so we actually have seen that a simple way to actually get out of this is epsilon greedy policy improvement, meaning that in epsilon steps, by a chance of epsilon, so the probability is epsilon to actually explore the environment. So with an epsilon probability, you will choose a random action, and with 1 minus epsilon probability, you will choose the greedy action. This actually guarantees you that you will keep on exploring the state space. We have seen that it doesn't make sense to actually fully evaluate the value function. We have also seen this with a practical example where it is sufficient to update the value function a little bit to already improve your policy, and you can hence use this, and you can update actually. You can just run a single episode to update your value function and then improve your policy again. And if you take it a step further, you can also do it each time step. And in this case, we ended up in Sarsa, which was the first on-policy control algorithm that we have seen based on TD learning, where you update your value function. So SARSA, you select your action from a state S you're in using an epsilon greedy policy, for instance, and then you end up, you take this action, you end up in a state S prime, you select the action using an epsilon greedy policy, and you will update the state action value in here with respect to the state action value of this one. We found out that this works really well in practice. However, there is a thing that you can do, which is actually saying that the target that we use to update our policy is not the greedy action, but it is really the max action that I can take with the best of my knowledge from the state, meaning that in order to update the QSA value from here, I will not use the QSA value using the epsilon greedy policy, which might not be the maximum Q value I can get, but it is really the maximum Q value, and I will update my QSA value in here, not with respect to the action that I actually take, but with the maximum, with the action the greedy policy would take. This essentially means that we have an off policy algorithm, meaning that we have a behavior policy that is different from the target policy, which, however, introduces a little bit instability because the general policy improvement, policy iteration framework actually assumes that behavior policy and target policy are the same. And there is also a difference of them, how they perform in practice. If you're interested in this, look the previous video, then you will get a little bit of information, or go to this link. There, they talk about this example very well. So if we actually compare Q-learning and Sarsa, Q-learning estimates actually the return, so the total discounted future reward for state action pairs assuming a greedy policy. So it actually estimates the return that you would get following a greedy policy while following an explorative policy, which is a really nice thing to do. And instead, Sarsa estimates the return for the state action pairs assuming the current policy that it also follows, which in many cases must be the explorative policy and actually to explore the state space. If the current policy is also a greedy policy, then the distinction disappears. So then Sarsa will actually be equivalent to Q-learning, with the exception that as the action is selected before the update, it might lead to a one-step delay between Q-learning and Sarsa at this point, but they are really similar in a sense. And Sarsa will also approach Q-learning if we decay the the exploration probability carefully. We also have seen a few advantages and disadvantages of both Sarsa and Q-learning. So both of them process each of the samples immediately and have a minimal update cost per sample, while both of them require a huge number of samples to actually converge to the optimal value function. Q-learning poses no constraints on the actual sample collection because it's off policy. So you can use any behavior policy to actually get information from the environment and update your greedy and update the Q function for the greedy policy. Both of them exhibit instabilities under approximate representation, which is something that we will address in the next lecture. Both of them have also the problem that the ordering of samples is really important because of the correlations between the time steps that we actually see when we run both of the agents through the environment. And also both of them make minimal use of each sample because in their current versions, both of them just use them to update the Q function and then they throw away the information. Okay, so more on this. We build on top of Q-learning a lot in the upcoming 2 lectures. I will give you also a teaser where we will end up in a few lectures ahead. So we will really see reinforcement learning agents that really are capable of playing games like StarCraft 2, where we will in the upcoming lectures talk a little bit about game theoretic problems where we have many good strategies, where we have imperfect information and really crucial information is hidden from the agent. We will talk about long-term planning where early actions pay off much later. So this is something we did not really yet look into it. So that early actions cost you maybe a little bit and the payoff for such early actions is really far in the future. And where we have really large state and action spaces. So state spaces currently are discrete settings in a grid world, and action spaces are 2, 4, 3, 6, 7, 8 actions that we can take. But however, what is it if the action space is 100 or 1,000 different actions that we can take? We will also see how to use many known tricks from the deep learning literature to actually also in reinforcement learning, how to use LSTMs, for example, and also how to use genetic approaches, evolutionary approaches or population-based methods, also to actually find good policies and controllers in reinforcement learning. So this is it so far. In the next lecture, we will talk about value function approximation.